And I'm going to step away from here for just a minute. And you can see that the original light that you would see is in the center and off to one side or the other are spectra. Okay. So, I'm getting a little, we're getting a repeat back over here, half-second delay. Okay, well, one of my heroes, by the way, here. This is a nice rendition that National Geographic did many years ago. Astronomer William Herschel in 1800 used a prism to see how starlight compares to the colors of Earth's sunlight. And you notice that different stars, of course, had different color patterns. And I really enjoy this picture because the artist got the idea right. There's William. In the background is the 40 feet, as he called it, which had a 48-inch mirror. Actually, there are 3 of them. I think 2 of them survive today. Terribly tarnished, but this is all hand polished to get the figure and such too. Young John, who would carry his father's observations of his general catalog, extended, and then Dreyer, U.L.E. Dreyer, I believe it is, in the late 19th century, ended up creating the new general catalog, but it started with William. And of course, Caroline, his sister, International Lady of Mystery. We really don't know what she looked like when she was very young. We have an engraving, I believe it's an engraving, and when she was quite old, I think maybe in her early 90s. But still sharp as a whip, I'll tell you that much. Okay. Noting that a red filter seemed to pass more heat than sun from the sun than other colors, he experimented with a prism and thermometers. Now, each of the thermometers you can see here rises higher as it approached the red end of the spectrum. And this is a key date in optics. February 11th, 1800, he moved the red lit thermometer further from the visible color calibrated to the surrounding room temperature, and it rose higher. He had discovered a wavelength hitherto not expected, the infrared. And in astronomy, the infrared is incredibly important. It allows us to be able to, for example, see star creation within a nebula. And there's a lot more uses to it. It's the first one I could think of. Okay. He also noted that, like visible light, the infrared could be focused and reflected. Did the same set of thermometers and be able to detect it. Okay. Now, inspired by his discovery, Johann Ritter and William Wollaston here, independent of each other, repeat the experiment in 1801 by using photosensitized paper, because the chemicals in the paper were known to darken in blue light. And sure enough, the paper darkened just on the other side of the blue for the ultraviolet. Okay, so here we have a fundamental question. Optician Joseph Fraunhofer wanted to understand the nature of light to help him make better lenses. He probably carried the art of making lenses maybe a couple of orders of magnitude higher than those before him. Believe it or not, optical testing and refractors back then was basically put it together and hope everything cleaned up properly. He wanted to test it. That's why his lenses in particular are treasured today, even as old as they are, because of that. Okay, so in 1814, he set up a prism to break up white light into a spectrum or rainbow and a little small telescope to examine the colors at relatively high magnification. And he saw as many as 545 of these fine lines dark lines crossing the spectrum. And they were not introduced by the instrument. He noted that several stars appeared to have the same dark lines, but in varied number and in prominence. He did not pursue the observation, but returned back to his optical work. He was an optician. He had to eat, essentially. But he died early, tuberculosis apparently, back in 1828 at the age of 39. And the problem languished until 1849, when 2 scientists joined forces to study the phenomena. Chemistry and physics united, in effect. Gustav Kirchhoff and Robert Bunsen discovered the basic rules that made these lines appear, found the connection and the placement of the lines to each of the chemical elements, and made the spectroscope into a tool of science. And essentially, that's a quick diagram of what they were doing. Okay, it's a bit of a groundbreaking discovery here. When they burned a chemical in a gas flame, they saw an emission or bright line spectrum up on the top there. But when the sunlight passed through the flame, the lines appeared in absorption. They were dark lines, but in the same places, allowed them to develop laws of spectral analysis, which explain the nature of what created the light. So here are Kirchhoff's 3 laws of spectroscopy. An incandescent solid, liquid, or gas under pressure, high pressure, emits a continuous spectrum. A hot gas under low pressure gives a, yes, that's right, bright line, or an emission line spectrum. And then a continuous spectrum viewed through a cool, low-density gas created an absorption light, or dark line spectrum. Now materials could be studied in detail, simplifying lab work, which I think is one of the really great things of this, because you can see, just want to make sure I got this, yeah, various elements, and they have different spectra. Yeah, in fact, yeah, very good. Exactly right. Light's barcode. That is so cool. I hadn't thought of it that way. Thank you. Okay, so Bunsen's comment. Okay. Oh, thank you. See, echo I'm getting a hope here. It's a little annoying, but there's nothing you can do about it. It's all right. At the moment, I'm occupied by an investigation with Kirchhoff, which does not allow us to sleep. Kirchhoff has made a totally unexpected discovery inasmuch as he found out that the cause for the dark lines in the solar spectrum. Here, the path is open for determination of the chemical composition of the sun and the fixed stars. This is groundbreaking. Oh. Okay. And maybe that'll work. Okay, sounds good. Okay, we'll give it a shot here. Okay, unknown on Earth. This is one of those incredible discovery things. In 1868, at a total eclipse of the sun, the spectroscope made a major discovery. A new element that was found first only on the sun and named helium, for Helios, the sun god. Later on, it was found in great quantities here on Earth, kind of almost a byproduct of oil drilling, which also indicated there must be a lot of uranium down there and other radioactives that decay, and one of the decay products just happens to be, you guessed it, helium. But this was the first time an element was discovered in an object in space, and that's thanks to the spectroscope. Now, for anybody who's a Star Trek fan, they talk about dilithium, and they talk about certain metals in the Marvel Comics universe they call adamantium, which is borderline to invulnerable, stuff like that. Wolverine's claws are made of this ridiculously strong metal. Still can't figure out how the heck to do it. But it's nice and it's fun, but has no basis in reality. This is hard reality. It was a complete surprise, this discovery. Okay. And visually observing spectra, Secchi's best efforts started the use of the spectroscope to excuse me, to understand the stars by their composition. And on the right, you see various spectra. And yeah. Vega, Altair, and Regulus to the top, and Arcturus and others, the next one. So this is really amazing. It was almost a celestial miner finding these materials up there. And the amateurs, not that I want to walk right past amateur astronomy, because I'm an amateur astronomer too. I don't get paid for this. And I'm rather glad for that too. I hate to see the taxes. But in the hands of amateurs, though, William and Margaret Huggins pioneered full-scale photographic study of the composition of stars. And a contemporary of his, Henry Draper, he pioneered the use of photography in spectra. He died at age 45, which even back then, in the 19th century, was rather young, would lead to the establishment of the Henry Draper Memorial Fund by his wife, Mariana, at Harvard College Observatory, and arranged to publish the catalog. Look at that number, folks. 369,083 star classifications to his memory. Now, that is quite an honor. Okay. And this young woman here, Wilhelmina Fleming, and the spectrograms for the Henry Draper catalog expanded Secchi's work into 23, she had 23 classes of stars. And for the first time, the ideas of stellar evolution just started to be a hint. And in additions and modifications, this young woman here, Antonia Maury, started to use spectra to understand the physical properties of stars, not just what they were made of. Speed, distance, physical size, and movement relative to Earth were found. And she also expanded Fleming's classes of stars. And the spectra also tells us temperature. If you look at the strongest colors or wavelength, the light emitted by a star, you can calculate mathematically its temperature. Okay, and here's, this, I'm going to sneak in front here just for a moment. Yeah, it does stand out. How do you like that? Various stars and their temperatures is calculated from the spectra. They are the spectra, and these are comparison spectra of known and non-moving, I might add, chemical elements. So you're able to see some of them, the cooler they are, the more complex the spectrum. The hotter they are at the top with Eta Orionis at 40,000 surface temperature, there's only the lines of hydrogen pretty much. So it's really an amazing thing. Okay, and the modern system. This is an older picture. She was near, I think she was about 10 years away from her death when this photo was taken. But it shows her in action with a plate of spectra. Yes, glass plate. Photographic film didn't come up until maybe the 1930s, really. She gave us the current system, which is based on temperature and luminosity, the brightness or energy output that we use today. Her insight is recognized as the model still in use today. Okay, so here is the modern system, and everyone remembers, oh, be a fine girl, kiss me, or guy, kiss me right now, sweetie, is the rest of it. But that little mnemonic applies, of course, right here. And this is the difference between the stars. You can see at the top, O-type, pretty much just hydrogen, and hydrogen lines, but relatively weak. Helium, though, starts heating up very nicely and making itself known. Carbon starts making its presence, then iron and type A's. And G, lucky us, our sun over here. So oxygen starts to appear. So you see, the cooler it is, the more elements we're able to see in being created within that star. Okay. And how do, or actually do, spectra tell us about movement? The old Doppler shift. I mean, driving here on Route 80, I heard a lot of Doppler shifts in car horns and such going by. Everyone gets it, but you know that sound? Yeah, there's your Doppler shift in sound. Of course, you know, that also occurs in light. Doppler shift happens, an object is moving toward or away from us, as in a siren coming toward us. Wavelength is influenced by the movement. It works with sound, with light, with any waveform. Okay, and the Doppler shift with light, and you can see on the diagram here that the further away the object seems to be from us, the more shifted to the red the light is. It's receding from us. And there's an old quote that said that from a well-known philosopher that said that scientists have discovered that most of the universe, stars, planets, galaxies, are moving away from the Earth on an average speed. He came up with a bad number of 15,000 miles per second. But then again, who could blame them? Makes you wonder. Philosopher is Alfred E. Newman. Okay, well, the Doppler shift, you can see the further away it is, the more shifted the light, and to the red. In fact, I believe there's only one object that at least I'm aware of, that gives us a blue shift. It's Andromeda, the Andromeda Galaxy. Must like us for some reason. It's heading toward us. So if you got the time, wait about 500 million years, and it's going to be right on top of us. Collision. So we'll see. Okay, and filling in the gaps, over the years, other forms of electromagnetic radiation were discovered. Radio, microwaves, X-ray, and gamma light all fall on a plot as above, their placement due to their wavelength. Okay, now today we use modern gratings, which are much more efficient than prisms. And of course, prisms have a nasty habit of absorbing some of the light that we want to look at. Quartz will let infrared through, and the ultraviolet, but it cuts off rather sharply. These are pure reflection. And this is a research grade grading. You're looking at, see if that's right. You're looking at a $750,000 grading, 3 feet long. Now, I'm going to ask a question at this point. Is there anybody here who is still teaching or knows some teachers and such? Everybody doesn't want to admit it. Okay. Well, I have diffraction gratings. Okay, great. Good, I'll talk to you. I have diffraction gratings with me, and I think we have enough for, I think we have enough for everybody. So you too can look at a bright light and have your own rainbow. But as I will say later in the talk, do not look at the sun. And I'll show you how to do that safely, because you've got to remember the thing is only 8 minutes away by light speed. That also includes infrared. And even that tiny bit that gets through here, as you are all well aware, could damage the retina. I don't want anybody getting a damaged retina just looking for, worshiping the great gods of light physics. No, we don't do that. Okay. And they're on just about every spacecraft. In 1946, the first spectrograph hit space and images the solar spectrum finally in the ultraviolet. Okay, and even Hubble has it. And of course, the James Webb today. So the James Webb really looks from the red into the infrared, and its mirrors are coated with gold, which reflects the infrared very, very strongly. But with the HST, it's got 2 spectrographs and advanced CCD cameras to image from near ultraviolet through near infrared. And the Mars Spectroscopic Laboratory maybe would have been a better name for this Mars rover, because it's got at least, and I got to remind myself, at least 4 spectrometers on it. Probably made the planet very, very paranoid. It's being studied that well. Now, for those who want to do experimentation, you can build a spectroscope. It used to be even building a prism one. The prism was the heart and soul of the instrument. Unfortunately, it's also the most expensive part. With modern lasers and with photographic film and such, we can make them very cheaply. So to build your own spectroscope, this is all you need: masking tape, the diffraction grating, and a paper tube like the core from a roll of paper toweling. Okay, you would take your grating, which is mounted in a photographic holder, the last use, I think, for slide film holders. Put 4 tapes on the diffraction grating. Do not touch the plastic grating material. Oh yeah, before I go any further, everyone, I think we got enough for everybody here. Everyone is going home with the diffraction grating of their very own. You're going to have it's a little 2x2, and you'll be able to look at various light sources, and I'll talk about the sun in just a moment. But put 4 tabs on the diffraction grating, and don't touch the plastic material on there. It'll still work, but it's going to kind of scatter the light, and it looks awful. Everybody sees your fingerprint. Okay, you tape the grating to one end of the tube and secure with a turn of tape on the tube. Okay, on the other end, you put 2 pieces of tape parallel to each other, leaving a slit as close as you can without overlapping, and then fill in the gap on either side with more tape. Okay, you put a piece of tape on the top and bottom of the slit, making sure it's about 3/4 inch length, and your spectroscope is done. Now, wasn't that easy? And there is the finished instrument. You too could are living with this equipment, a living spectrophotometer. You can look at light, you can look at broken up various light sources, and then be able to calculate approximately what wavelength it is. You don't have to be very accurate. That line there is red, that one over there is green, this one's blue. That's a funny looking indigo, stuff like that. But you can do it. And what you will see is this. You point at a light source. That's a 0 order, as it's called, of the actual object you're looking at. And then toward me, minus and plus would be the order of spectra. And this, you're looking at a fluorescent lamp. And you can try other light sources to see their spectrum. And warning, and I really mean it there. It would be pretty much a continuous, yeah. You will see, if you had magnification on that spectrum, you'd be able to see some of the more prominent dark lines. If the sun ever gives emission lines other than a solar prominence and such, where the hydrogen gas is glowing, it's probably got a bit of calcium in there too. The sun starts giving out everything in emission. Get on your starship and get out of here, because the star is about to blow, because that's what's happening. The energy is coming out. Okay, but again, though, I warn everybody, do not point this thing up at the sun. Catch a reflection off a piece of white paper in full sunlight, or from an uncoated piece of glass. At least you'll have a fighting chance of noticing those colors are really bright and move away. Or from a reflection from a large needle. And don't use a mirror. I've seen people goof up with that, and they wonder why they have this blue image of the sun for the next hour or two. They're lucky they didn't have any damage. And for those who really want to learn more about this, here's a little bit of information. This is not really a new book. It's been around for some time, but I think I dare say that it's as new then, and it's very, very new now. This is it. European amateurs have been way ahead of us for quite a few years. This particular book, Astronomical Spectroscopy for Amateurs, brings the science to this side of the pond, as they say, just as the new technology have gotten more inexpensive. And new tech, the star analyzer is still available. You can look it up in Sky and Telescope. And its associated software make it very affordable for the amateur astronomer to become a backyard physicist. I bet all of you didn't realize, with your telescopes and such, you are budding physicists ready to explore. All you need is just a little bit more technology. And there it is. This is a much higher precision diffraction grating from the ones I'm going to be giving out today. Yes, you're all going to go home with your own personal diffraction grating. Okay, and this is what it looks like. This is not how I look at my bedroom window after a very bad night in a bar, but it seems to be that distorted. By the way, you'd never find me in a bar. Okay, those who want to do higher aspirations. Now, this is actually a little older, although there are better models from the same company. Lahars gives you the best moderate cost spectroscope or graph that's available today. I think the price now is just under $2,000, but that's not bad considering originally some of these things are up in the 10,000s and more. Okay. And one more photo. There's a story behind this. Sometimes I get diffraction gratings. You can get them from, used to get them from Edmund Scientific. I think you still can, but there's a place called Rainbow Symphony, which makes these all the time. That's all they do. Holographic gratings, and the cheaper ones are their bread and butter. So there was the daughter of a good friend of ours, and Susan. And Susan was, I was talking with her, and I said, I have these diffraction gratings. And she was saying, this is great, because see, I heard her mother's tale of woe. I need a violin in the background here. But Irene, her mom, told me that they were taking one or two of these little diffraction gratings and cutting them up into little pieces. And I'm saying, this is not the way you do science. I'm sorry. So I went Rainbow Symphony. I bought a bunch of the gratings, which are cheap. I think they're nowadays, I think they're about 75 cents a piece, something like that. In that ballpark, very, very cheap. And then I got a sheet of it for I think another $5. And the sheet's about like this. So here I am, innocent me, and she's flipping out. Oh my gosh, look at this wonderful grains. Thank you. And I say, you think that's good? Look at this. And I pull out this sheet, which is 5 by 11. Hold it up, and as I'm doing this, I'm looking through it. This is at Sperry Observatory down in Cranford, where AAI has its headquarters. And I'm looking down the hallway here to the kitchenette and the lights. And you can see in this picture that we got catching two spectra. I'm going to step away from here for just a moment. Yeah, and here you are. Here you have, when they used to put mercury lights up there, there is the mercury line spectrum, rather crude but effective. And here's an incandescent bulb, a hot metal glowing. And I saw this and they said, okay, Sue, hold this. Don't move. Girl went to statue. And I grabbed my camera, came over and took this photograph. So this is a continuous spectrum, and there's your bright line spectrum, all in one picture. Quite remarkable. Oh, and she liked the grading too, by the way. Oh, okay. Oh, I don't know, actually. Okay. It's okay. We're almost done anyway. Thank you, though. Okay. So like I said, she was happy. I was happy. In fact, I was astonished. I hadn't even thought of this. Okay. Okay. What happened here? There we are. Okay. And an observation. There we are. Astronomy, the oldest of sciences, has more and renewed her youth. At no time in the past has she been so bright with unbounded aspirations and hopes as William Huggins in 1891. I wonder what day of that year he wrote this. Okay. And I'd like to thank Bonnie, who manages to make my pictures will come to life. Mary Lou West, the chair of AAI Research Committee. Michelle Tofu is educator, inspiration, and of course, Susan Greenstein, educator, inspiration, and of course, NASA. And I believe, yep, that's it.
Yeah.
Okay. So if we could get the lights on in here. Oh, yeah. Oh, yeah, coming up. Excuse me, Mike. They caught me with the spotlight. Okay.
Good.
Okay. All right, first things first, are any teachers in the room? Any educators? Oh, well, so much for that theory. Okay. Oh, over there, hi. What we're going to do is, first things first. Here you go, sir. This is taken straight off the building of Spectroscope, that section of the talk. Okay. And by the way, for those that were curious about it, this is what the spectroscope looks like when you've assembled it. So the slit's over here, this is over here. And I'm going to pass this around. We have a beautiful, this is terrific. This is all coming together. That white light, you can all look through here and see the spectrum. I'm going to start over here and just pass it on down the line. You know?
Saved me $10. I was going to buy one on Amazon.
Oh, well, you can do that too. I get a kickback of a whole penny. Okay, let me see what I got over here. All right, so I'll start on this side over here. Al's goodie bag over here. Okay. I beg your pardon? Oh, I've been needing help for years. What I'd like to do, and you knew that was coming. What I'd like to do is give one each of these to everybody here, and we'll probably run out of this. There are a group of 25. When you get these, please hold them by the edges, kind of like that, and you can look into the lights over here. Okay, thank you. But yes.
So you mentioned the scientific company.
Mhm.
I think now it would still be Edmund Optical Company. The scientific part was sold about 25 years ago.
That's right.
To a company in 101 that you wrote is now out of business as well.
Mm.
So, but I think maybe I haven't checked their inventory, but I guess we can check and see if they still offer the refractor. I got those ages ago when I was a kid.
Mm-hmm. Yeah, I got one of their good reflection half inch. Was all I could afford.
They sold
Too
some
much.
great Christmas too.
Yeah. Oh yeah. Yeah, they were originally called, by the way, Edmunds Salvage Company. Right after World War II, they grabbed all the wonderful surplus optics that they didn't need in beating the Hun. But yeah, yep. I remember driving all the way down there. We'd go to Denton Vacuum to get my mirrors coated. And while I'm waiting an hour or so for it to be set up, I go there and go broke. Between Ed Sy and the mirror coating, I went home with just enough money to get gas. That was it.
One time I went down. Don't get lost.
Yeah. Oh, gosh. Okay. Now, let's see if we can do this. Okay. All right. I guess everybody's got a, yeah. Okay. Everybody's got a diffraction grating. One of the gratings. I don't know if it will work very well. But I'm going to hold this up. This is a fluorescent battery operated light. And if you look at it through there, you might be able to see the lines. A bright line. I may have to turn it 90 degrees. There you go. But you should be able to see at least something from it from here. There it is. Yeah. These over here are probably a halogen, so they're going to have a, it's called a continuous spectrum. This will give you the bright lines as well for mercury. Okay. Nick, I think next time I do this, I'm going to get a much larger one. This is, I'm used to using this. I'm used to using this at home. Okay. All right. Now to take your specimen home, just pass around the these envelopes. They will take one or two and pass the rest. I'll start the other side here. Okay, and I'm going to put these over here, and just this is a holder to put your grading in, so you don't get fingerprints or other people say, "Oh, look at this." That's happened more times than I want to tell you about. Okay, I think that's about it. Okay, so I'm going to ask one more time. Do we have any teachers in here that's still working and such? Oh, him. Okay. Hi, you. Okay. Okay, you got one. Okay. All right. So I have two extra over here if anybody's interested in instructions on how to build the spectroscope that we were passing around. Oh, come on. Don't be shy. Let's go physics. All right. Okay. So are there any questions? To be honest with you, it's about the same kind of impact that astronomy in general is feeling with it. I personally am very leery about AI. It's still in its infancy. I mean, you're not going to have computers that are going to launch missiles to get rid of the silly humans and such, but I think that it's going to change our way of thinking in general. That's about the only thing I can say, comment on it. Mhm.
Billions and billions of pixels of data.
Mhm. AI will come in real handy. If it holds to its promise, it's going to be fantastic. I hope.
Any more questions?
Any more?
None of us?
Everyone's totally. Thank you. We try. Yep. Okay, thank you.
Library. So, okay. You wouldn't get your grade.